In this simple example, we'll be asking the following question. Okay, suppose you have users all uniform. They all look the same with a certain utility function, which is a weighted log utility function for a certain given capacity bits per second measured, okay, denoted by x. I look at the log of x weighted by sigma. Okay, so sigma parameterizes basically now the log utility functions. And the user, the carriers, is charging a price based on the consumption amount. This is a typical chart we've seen. There's a flat rate component G dollars. It doesn't matter how much you consume, plus a usage-based H dollars per amount of consumption. Okay. So now if I look at the graph, it looks like this. Okay, this is G dollars, right? And this part is H dollars per unit of consumption, say per gigabyte. So I'm going to look at these two functions. On the consumer side is the utility function sigma times log of x, and on the carrier side P of x G plus Hx. And I'll ignore this horizontal shift in the demand, because by paying G you actually get a fixed amount of up to a certain fixed amount of data. So I'm going to ignore this to simplify the notation. It does not change the gist of either presentation or the conclusions. So question number one, given the baseline usage price, that's given G dollars and H dollar per gigabyte, what is the demand? And second, given such demand, how to optimize the price. Now you see this feedback loop, right? Consumers have utility functions. Carrier decide a price, right? You give a different price to consumer, they give you a different demand, and then that will shift your price again. Now this kind of loop we'll see a few times. We will see it in TCP, in a network context. We'll see it next lecture in SDP, smart data pricing, in a more elaborate way. And the general notion of you design something and then the agents will react was certainly even broader in its applications, as we have seen in auction and so on. All right, so let's write down the equations. First of all, on the consumer side, you say that, you know what, I'm going to look at my net utility, which is sigma x log of x minus the price was G plus Hx. Okay, this is my net utility. I will set as derivative against x to be 0. What is the derivative? Well, it's just sigma over x minus h equal to 0. That means my x star is just sigma over h. All right, that makes sense. Bigger h, steeper slope, I consume less. How much less? Well, governed by sigma. Fine. This is the answer. By setting the derivative of net utility to be 0. Now, what about the carriers? Price setting. That is the G and H setting. There are two parameters for you to play with. The baseline and the slope. Well, in this case, you're not setting the derivative to be 0. Instead, we say that this is a monopoly carrier. It has a price setting power, meaning that it can squeeze your net utility itself, now the derivative itself, to 0. This assumes that this is a very powerful carrier. It got the price setting power, meaning that it can set the G and H such that your utility is 0. This is clearly an extreme case of modeling monopoly power. It's not realistic in our mobile data market, but for a simple illustration it suffices. Okay, so this leaves no utility to the consumers. It can be negative because it's negative, the users won't participate. Okay, and to properly use this monopoly price setting power, we'll set it to be 0. So we can solve this second equation. The second equation says sigma log of x equals G plus Hx. So now I've got two equations. One is by the demand modeling, the other is by the monopoly price setting modeling. We can stick this x into this equation, and now we have the following result. Sigma times log of sigma over h equals g plus h sigma over h equals g plus sigma. Okay. That means we can set the flat rate g to be sigma log of sigma over h minus 1. Now this assumes that you know that as a carrier, you know the consumers are taking the log utility function with a known sigma value, which again is unrealistic to assume, but let's say that's the case now. So now we have the answer. Okay, so you give me a sigma, okay, and then I can pick out a h slope, then that will give me a g. For example, let's say sigma is set to be 100 unit. All right. Then let's look at two cases. One is when h is $2 a gigabyte. That's the slope. Then plug in the equation sigma and h, you get the g, which is the flat rate, $70. All right. So $70 a month as the baseline. Then extra gigabyte, you pay $2. This implies that the revenue for ISP, G plus HX, equals $170 a month. Okay, and the flat rate component is 41% of the total revenue. Case A. Case B. Suppose I increase H now to $5 per gigabyte. Okay, then plug in the equation sigma is 100, H is 5, G is 30. That means an alternative is to set the baseline to be $30 and every gigabyte get $5. This actually is quite close, reasonably close to the actual pricing points used by AT&T Verizon Wireless. This implies on average the ISP, monopoly power ISP, under our assumption, gets $130 as the revenue, and the flat rate component is now only 23% of the total revenue. Now you can look at many more cases, but you get the trend. The trend says that actually you should make H real small, okay, very shallow slope, okay, so that you can afford to make G, the constant part, very high. This will max out your revenue, and the flat rate part will be dominant. Okay, now say that's actually somewhat counterintuitive conclusion, isn't it? Indeed it is. That's because we have made the three unrealistic assumptions. Number one is that we assume there's only one bottleneck link. In lecture 14, we'll take this away in TCP congestion control at much faster time scale than monthly bills. Number two is there's no capacity cost or constraints of any kind. And that was the fundamental reason why we got that somewhat counterintuitive conclusion from this simple numerical illustration. Once we put capacity either as a constraint, you can exceed a certain capacity, or as a cost, then you see that we cannot make H arbitrarily small and G arbitrarily large, because that will induce a tremendous amount of traffic that will violate the constraints or increase the cost to the point of not making it worthwhile. The last one is that ISP was assumed to be monopoly, and therefore price setting power to squeeze your utility as a consumer to zero. This is unrealistic. So later in the course, we'll perhaps still keep this assumption, but certainly remove these two assumptions. In fact, in the advanced material, we'll remove this assumption. In lecture 14, we'll remove this one. Now, having gone through this perhaps unrealistic small numerical illustration, let's highlight that we did touch upon a very important conceptual and methodological tool called utility maximization. It generalizes the payoff function ideas we mentioned before. So far, we haven't seen network because there's no network constraints or coupling yet, but that's coming up in lectures ahead. This utility maximization models consumer behavior. We've seen utility function, demand function, and induced elasticity of demand. We've also seen a very, very powerful notion that the pricing whether it's on a single link over network, it can coordinate demand versus supply. Whether that's done on a monthly bill time scale or 50 millisecond round trip scale of the internet. Whatever time scale, if you can design a proper pricing, then it can help just demand supply. Just like we've seen proper pricing in auction, like second price, can correctly internalize certain type of negative externality. But improper pricing can also create a tragedy of commons. Finally, for the specific topic of why usage-based pricing, well, you know the answer is because of jobs, inequality of capacity. Where do we go now from $10 a gigabyte? Is this the end of story or more? We'll look at smart data pricing in the next lecture.